Imagine you come home and your partner points her finger at you asking, "What's happening with our money?" You're surprised because you didn't realize there was a problem with your savings. But then she shows you this chart, which indeed looks disturbing. Since you don't recall a problem last time you checked, you open again the balance of your bank account to see this chart. And now you understand the problem. Although the data is identical, the format of both graphs is different. They convey different messages. Hence, it's not solely the data here, but to a great extent the perception that is communicated. Probably you will respond now with, "Yeah, I knew that." But do you? Whenever you analyze fatigue crack growth data, do you realize what the format of your own chart is doing with your own perception? Let us look at the following example. We have an object that travels along a straight line which started with an initial velocity. Now we measure the distance of the object that it travels as a function of time. We can do that for say 3 initial velocities to obtain the following data set in a graph that will look like this. Now we are interested in making predictions, so we are looking for a format that we can work with. So let us plot this graph in a double logarithmic form. Here's magic moment number 1. Whenever we see an apparent linear trend in our graphs, we tend to get excited, indifferent of the scales of the graphs. So we draw trend lines through the data and get the following power law functions. There's an influence visible of the initial velocity, so let's call that the initial velocity effect. Now to get to a prediction model, we can generalize the power law function to this simple equation in which both the capital C and the exponent n are a function of the initial velocity. So we plot both against the initial velocity and we get trend lines. Now the advantage of Excel is that we can evaluate different trend lines to find the best fit. Here's magic moment number 2. If the R-squared value is high, say above 0.9, we are generally satisfied. This trend line must be good. And now we can make predictions, so let us draft a paper on the assessment of the initial velocity effect in describing the distance of an object traveling along a straight line. However, there is another approach to this problem. Apparently not only time is the governing parameter here, but also the initial velocity. So when we go back to this graph, we can try to find the parameter in the x-axis that includes both time and the initial velocity. Here we are, with time times square root of initial velocity, all 3 curves collapse. And this is magic moment number 3. When multiple curves collapse to a single curve, we really get excited. So we have now the governing parameter, which must be correct because those curves collapse. And what we now do is we plot again a power law through this data to find the C and N values. Now for this given case, both parameters apparently have the same value, which brings us to the 4th magic moment. If certain parameters clearly relate, then there must be something correct in what we do. And now we can make predictions, so let us draft a paper on the assessment of the initial velocity effect in describing the distance of an object traveling along a straight line. However, based on that paper, someone else performs similar test, but measures displacement for a longer duration of time. Looking at their data, it seems the initial velocity effect that we identified is vanishing when time increases. Hence, predictions with our equations don't work well in the large time range. There appears to be a limitation to the range of our equation. How do we deal with that? Well, let us get back to the physics of this problem. The problem of an object traveling in a straight line is generally described by the following equations of motion. So let us focus on the equation for the distance and compare that to the equation we just obtained. We are missing a parameter here, the acceleration a. So the original data plotted on the original graph could have been fitted to the equation of motion, which would have revealed that the acceleration apparently is 0.5 meters per second squared. And that is what we missed with our standard approach for fatigue damage growth assessment. So next time, when we plot those well-known Paris curves illustrating a stress ratio effect, we have to start paying attention to what we do. Instead of getting excited when all these curves collapse when plotting against some sort of effective delta K, we should start doing our research and ask ourselves the question, what is the physics of this problem?